Hi everyone, my name is Jimmy, and I'll be going over some more advanced Atomate usage for the next hour. And Eric, who did the last lecture, will be my helper during this session. So if you have any questions, just put up your red stickies or flag down Eric or one of the other blue shirts around you, and they'll be able to help you. One of the things that I kind of want to just reference back to Eric's talk is what a workflow and what a fireworks is, and kind of what's the distinction between this package called fireworks and this package called Atomate, right? So a workflow is essentially a collection of independent fireworks, and they each could be either a VASP calculation or some kind of structure manipulation that you would do in Pymatgen, right? And a workflow is just a collection of all those things that may or may not be interdependent on each other, right? The fireworks package is a independent package that's meant to run sort of automated tasks on a supercomputer. So it can aggregate the inputs and outputs of various tasks that you might need to do on a remote computer, right? And it'll cache all of the information about whether those tasks completed onto a Mongo database somewhere, right? And Atomate is essentially the package that takes advantage of the tools that are built into fireworks and adds in some quantum chemistry specific interfaces. So if you want to use fireworks to run VASP calculations, all of the additional code that you would need would go into Atomate. Right, so this is kind of like the general framework that we've built, right? And in this specific lesson, I'm gonna show you how you can create and manage a very large number of Atomate workflows. I'll show you kind of in more detail some of the more advanced workflows that we've built into Atomate, and I'll also show you how to create workflows after they've been created. How to manipulate workflows after they've been created, and this was a question that was brought up at the tail end of the last session, like how would you modify the in-cart inputs into a in-cart input for a VASP calculation. And then finally, we'll run one of these large set of VASP calculations and analyze the outputs. Okay, so lunch break, yay. Okay. All right, so before we kind of get started, I want to make sure that everyone has their Pymatgen MAPI key populated inside of their system. So if you can just run this first cell, what that does is it populates your system. You should use your own personal key here, and this cell will also load some basic helper functions. These three helper functions that will come up later on during the talk, and I'll discuss each one of them as we go on. Okay, and it's very important that we have this MAPI key loaded on, because we're going to be querying the materials project database quite a bit during the process of this talk. Okay. Yeah. Oh yeah, and also I want to make sure you guys have the 2- workflow management and analysis with Atomate -empty notebook open, and that's the notebook that we'll be working on for the remainder of this hour. Okay. And so if you go to the next cell, right, you'll see some familiar objects here. So we're loading the Launchpad object that Eric used in the last lecture, right, as well as the MP rester, which will instantiate and call it MPR, right? And we'll call this instance of the Launchpad LPAD, right? So before we kind of continue, I just want to make sure that everyone has a working materials project query. So if you can type below MPR dot, npr dot get structure by material ID mp-149, right? And you should return a 2-atom silicon cell. So if everyone can do this on their system, right, then we can continue. Okay, this is just a quick verification. All right. Okay, so no one has problems with this. All right, so the one new function that we've loaded here is this get workflow function, which is from the VASP portion of Atomate, right? And if you so if you go into if you're hanging on a cell, you can press B to create an empty cell below it. And if you type get workflow, right, and you get the help for that, you see that this function, it takes a structure object and a workflow file name, right? So this workflow file name is something that's already hard-coded into Atomate, right? And if you want to look at the different ones that are available, so inside of this documentation, it'll tell you you can use these different YAML files that are hard-coded into the Atomate library. And if you go to if you go onto the Atomate GitHub page, and you can always get here just by Googling Atomate band structure.yaml. Right? It'll always take you here, and then you can go up one level into libraries. Right? So this is a collection of the different workflows that we use at the materials project. Right? And this band structure workflow that you've already seen, right, is in the last hour is composed of a structure optimization firework, a static firework, and this firework has a parent that is the 0 index firework, which was the previous one, right? And then after you complete the static calculation, you do a non-self-consistent calculation on a uniform k-grid and another non-self-consistent calculation on a grid on a line through your through your Boolean zone, right? So basically, we can use this YAML file, right, and to build our own workflow. So basically, so how many people here are kind of regular VASP practitioners? Right. So okay, it's about a third of the room, right? So okay, so let's say, so kind of a quick example of something that you might need to do in VASP, right? Like if your advisor told you to calculate the band structure of every single polymorph of silicon oxide, right? So without this kind of this large infrastructure that we've built, you would need to, go onto the materials project or the ICSD. You have to get all the CIF files for all of these different materials, and then you have to kind of use your own infrastructure to convert them into VASP calculations, run those calculations, and then analyze the outputs, right? So here, right, if we use this get workflow function, right? Sorry, and then if we get a structure, sorry, all right. So if we get a structure using the materials project query, we can use the get workflow function. Whoops. And call that with structure as the first parameter and the band structure.yaml as the second parameter, and that will create a workflow for us that will calculate the band structure. So that's how you do one silicon calculation. So I want you guys to spend a couple of minutes and think about how you would actually use the tools that you've seen here to to get the band structure, to basically create the workflows for all the different band structures of the different polymorphs of silicon oxide. I'll give you guys maybe three minutes to play around with that. All right, if you have any questions, just raise your hand. So I think in the interest of time, I can work through the answer here, and after I work it through, if anyone in the audience still has problems getting anything working, please put a red sticky on your laptop, and one of the helpers will come and aid you. Okay. So to do this, we need to first get all the different structures. So structures is equal to MP r.get structures. Right, so this function returns all of the different structures with a given chemical formula. So we can do SiO2. Right. Okay. And then all we need to do is iterate over this list of structures, create the workflow for each one of these, using each one of these structures, and then add them to our launchpad. So for structure in structures, workflow is equal to get. We can just really copy this. And then lpad. Right, and we can add this to our launchpad by using lpad.add workflow. So one thing, so that works, right? Yeah. So we see we added all of these workflows, and if we go to our Fireworks dashboard, right, we see that we just added 1,000 workflows for calculating the band structure of each phase of each polymorph of silicon oxide. Right. And this is kind of an illustration of the power of this entire high throughput framework, right? Because not only can you aggregate a lot of data really quickly, you can analyze the trends using this data, and additionally, it really allows you to keep the provenance of a calculation, because you know exactly how each calculation was submitted, where each calculation was performed, right? Because like as you kind of go on and doing materials research, just doing the bookkeeping ends up taking up a significant portion of your time, right? So, okay. So if everything's good, I will continue on. So before we move on, we need to reset the workflows database, because we don't plan on running those 1,000 calculations, because first, we don't have a real supercomputer, and we haven't written up the fake VASP outputs for all those things. So you should so we can use lpad.reset here. So it's important to remember you never really want to do this in production, because even your failed runs might tell you something about about either your computer setup or the system that you're studying. But we'll run that here. All right. Okay. So we just reset and cleared our launchpad. Okay. So let's get back. Okay. So one of the canonical examples that we always use when we talk about complex workflows, right? Because not only have we not only can you do many sort of basic workflows at the same time, you can also do one workflow that is very complex and has a lot of interdependencies, right? And the example that we'll use is the elastic workflow. So we'll first get the So we'll first get the structure of silicon with the conventional cubic unit cell. Sorry, this comment is a little bit long. It should show up fine on your notebooks. So structure And silicon is, of course, MP149. This is the code for silicon, but if you type in the name silicon, it should also work here. Whoops. Guess structure, sorry. Auto-completed to the wrong thing. Okay. Yeah, so, okay, so this is the base material that we want to perform the elastic workflow on, right? And we can view this, whoops. Yeah. And we need to get him using the conventional unit cell. So you need to set this flag, conventional unit cell equal to true. And this gives you the 8-atom silicon cell. And if we use this view function, right, we can, this is just a alias for the Crystal Toolkit viewer that you guys have been using in other parts of this workshop. Right. You see this 8-atom unit cell of silicon here. Right. So if we want to calculate the elastic constant for this material, we can import the elastic constant workflow, right? First, as well as this kind of stripped down, simplified version of the elastic constant workflow called elastic constant _ minimal, right? And if we just look at the sort of the help text, the doc string of this, right? We see that it takes a structure, right, and then various configurations that all have default values populated. So for basic calculations, we don't need to worry about those. So if we pass the silicon structure to this, we can create whoops. Okay. So now we created this workflow, right? One of the ways we can analyze what's happening in this workflow in a little bit more detail is using this little helper tool that we built into our workshop, which is this workflow to graph, which will take a specific workflow as the input, right, and kind of display all of the different fireworks. So that's the kind of individual things that this workflow has to accomplish, right, along the way. So if you, I apologize, this is very long, but you see, like, it's all doing the same thing. It's just doing multiple replicas of it, right? And if you kind of explore this workflow, you see that it really has a single root firework, which is the structure optimization, and a single leaf firework, which is doing the analysis. And in between, we have a bunch of fireworks that are different elastic deformations of the 8-atom silicon cell. And they basically each represent a transformation that you have to perform, and then you basically get the stress and strain from that calculation, and then you can populate it. So that's how we kind of examine the overall workflow, right? That's composed of different fireworks. But another thing that we can do using our workflow to graph function is we can examine each one of these things individually. So really, if we want to basically see what each fireworks in this fairly complicated workflow is doing, right? And one way to help us do that is this dir function, right? And this might be helpful for you because as you've seen in the last lecture, right, you have a workflow and the individual fireworks, they're each, so a workflow has a fireworks property, which is basically the full list of different fireworks, right? And this is essentially a list. So the 0th entry is just the fireworks with with number 0. However, if you're working in a Jupyter notebook, after you've kind of called a list like this, you can no longer tab complete, right? So this is kind of annoying if you got really comfortable doing this. So one of the things that you might be helpful, just kind of in the future as you explore more complicated data, is this dir function, which gives you all the various kind of member functions and properties of a Python class, right? So in this one, we have something called a name. So we know that if we say workflow dot fireworks 0, so the 0th firework dot name, we'll get something. Right, so this is the initial structure optimization, right? Okay, so now, and then we can print the, so using the workflow to graph function, we can print what this looks like. All right, so this is what the first firework looks like. It's composed of a whole series of tasks. So you basically write the VASP inputs from your Pymatgen default set, right? And then you run, you see that it runs VASP. You don't need to understand what all these functions do, but you can find references for them in our documentation, right? And then it passes the directory where the calculations were performed to maybe the next firework that would need it, and also it finally stores the outputs of the VASP calculation into a database, right? So that's basically how you explore the first firework, right? So now we can look at the next firework and the last firework. So. And if you go back to the graph, the first firework is this guy. The next firework is SI elastic deformation, and the final firework is this analyze elastic data. Right. Whoops. So the next firework, we see that it copies the VASP output from the location that it was passed to from the last time. It does some kind of transformation to the structure. So this is where you apply the stress, and then it runs VASP and does the similar type of thing. And it also passes the relevant results to the final step of analysis, where the workflow actually calculates the elastic tensor. So if we look at the last firework, so the last item in a list is indexed by -1 in Python, right? So all this does is it gets the elastic tensor and stores it into a database. Okay. So is everyone still on board? Okay. All right. So so if you look at this kind of standard elastic tensor workflow, right? You're doing a lot of calculations for a fairly simple material like silicon. And what this does is it kind of has a lot of redundancies, and it reduces the numerical noise of the calculation. You can actually get most of what you need using way fewer calculations, and that's what's in this elastic constant minimal workflow that we've built, right? So if you pass the exact same silicon structure into this elastic constant minimal workflow, right? Now you get a new workflow, and if we want to display the graph of that workflow, right? You see, this is much simpler. It assumes you already have a good structure to begin with. It just performs two different deformations one that's along the x-axis, and it assumes it determined that the y and z-axis will give you kind of similar results if you deform along those, and a single kind of shear deformation in the two other directions after you deformed in x. So this is considerably simpler. So we can kind of use, so we've basically did the calculation somewhere else. We cache the inputs and outputs into our workshop directory, and we can use this use fake VASP workshop, which is very similar to the use fake VASP that you saw in the last lecture. Right? We can use this to modify our workflow and then run it and look at the results. So if we import this, right, you can basically apply this. And we just do a sanity check, right? So our workflow is this silicon elastic constants workflow, right? And if we apply this use fake VASP workshop function to our workflow and then add it to our add it to our database, we see this kind of way more simplified version, right? Where we perform two different elastic deformations and we analyze the elastic constant. Okay. So now we basically have this set up, right? We can either run this in the notebook, right, in using kind of the Python fireworks interface, or using qlaunch as you've seen in the last lecture. So the following code snippet, if you just press Shift Enter, what it'll do is it'll create a temporary directory to put all of the input and output files, and it will pretend to run VASP essentially, right? And if you go back to your fireworks web GUI, you see that all of these things have finished running. Okay. Okay. So that's kind of how you build up a kind of simple workflow, and how you kind of go into each workflow to figure out what the individual steps of a workflow and a firework is doing. And one of the things that was brought up during the last talk is how do you kind of modify a workflow. Say if you want to like add modify a specific VASP parameter. And the way that's done is using what's known as power-ups, right? So these can do a lot of kind of commonly desired things to a quantum chemistry calculation, right? And the one that we're going to be focusing on is how do you kind of just modify the incar, which is the primary input file of a VASP calculation, right? So we'll go back to the example of the band structure calculation. So if you press escape, these actually should be in 2 cells. So you can copy this and paste it in the cell below. So if you kind of print the first firework, right? So the firework with index 0 of this band structure YAML of the standard band structure calculation, you see that this is something that we already saw a little bit earlier. However, if you call this add modify incar function with the original workflow as an input, but also a dictionary that tells it you're updating the incar with a new energy cutoff value, right? So this is ecut. All right, this new energy cutoff value of 700, right? You can run, so if you create this new modified workflow, you can see that inside of the first firework, right, in between where it initially wrote the first the the first version of the in-car, it has a modified in-car task, right, which has been inserted before you need to before you actually run the VASP calculation. So this is something that will be basically applied to every single firework inside of your workflow. So I want you guys to maybe take a little bit of time to kind of explore this particular firework that we built, right? So so maybe if you guys can kind of find different parts of the workflow where this in-car update task sits, and basically if you can examine the workflow and find out where this value is actually updated. So if you can print the new in-cut is 700, right? That would be great. So if you guys kind of spend a couple minutes to just dig around inside of this modified workflow object and see if you can find where the update of the in-cut value actually happens. Okay, so yeah, let's have a look at this. So if we have the modified, so if we have the modified workflow, all right, and we have the different fireworks. So if we want to look at fireworks, if we want to look at the second firework in this case, right? Once again, we can use the workflow to graph. Whoops. Yeah, there's an S here. Yeah, can use the workflow to graph, right? And we can see that the modified in-car is inserted as the third task. And if we want to examine a specific task, we can actually say modify fireworks 1, and then the tasks are a member of this object. And if we look at the third task, which will have index 2, right? Whoops. Right, we see that this is a modified in-car object, and this is exactly where in the fireworks data this update to the e-cut value is stored. Okay. So yeah, so that's how you use the add in-car update power up. And so as you start running more and more of these simulations, right? And you really need to explore like the results of your simulations, you might find that it's kind of inconvenient to have all of the calculations just sitting in one big database. So you might need to, based on your specific usage scenario, add different tags to the various calculations. So we'll first import this add tags power up from Atomate. Right? And if we look at the original workflow that we built earlier for the band structure of silicon, right? So this is before we modified it with the new in-car parameter, right? We see that this workflow doesn't have any internal metadata, and the last task for this workflow just looks like this. So it inserts the material into the database with the following keys that's passed as a dictionary. So you don't need to worry about too much about what these things are doing, right? But these are just information that's being used internally by Atomate. So I want you guys to look at the documentation of this add tags function and try to add your own personal tag to this workflow, right? And I'll give you guys a quick minute to do that. Okay, so if you so let's look at the documentation of add tags, right? We see that it really just needs a one original workflow and a list of tags that you want to be inserted. So we can pass it the original workflow and a list of tags. So we'll maybe tag our things if we're studying photocathodes. That is not how you spell cathodes. All right, and then the new workflow will just be will just be the results of calling this add tag function. And if we look at the metadata and the last task again, we see that in the metadata, this tags has been populated, and then inside of the last task, which is this vast to DB, we're now updating the database entry with this photocathodes tag, right? So this is basically what you would do to organize your calculations once you start doing many more of these. Okay. So now let's kind of take a look at some other kind of more complex workflows that you might find in Atomate. So the one that we're going to look at right now is this get workflows for all slabs workflow, right? So this is something that's going to, let's say if we want to do a calculation to determine the hydrogen absorption energy on various different facets of a material like plutonium, right? We can use this workflow to automate that process for us. So, to be able to accomplish this, right, we'll first need to get the unit cell of plutonium. So plutonium will be, we'll use npr.get structure by material ID, and then plutonium, right? And then once again, we'll use the conventional unit cell. Right. So this is an example of us passing not the actual materials project ID of a material, but the name, and this still works just fine, right? And the adsorbate will be a molecule. This is a object that you might be familiar with from Sam's talk from yesterday. Molecule. And this molecule will be a hydrogen molecule, so it's got 2 hydrogen atoms. And let's put one at 0.9. And then it needs to be a list of these. So the first entry is at 0, and 0.9. And the second entry will be at 0.9, but with a minus sign. Right. And then just for a sanity check, let's view the adsorbate. Okay. Yeah. So there we have our hydrogen molecule. Right. And I want you guys to take a minute. Look at the documentation of this get workflow for all slabs. Get workflow for all slabs, and using the 2 structure and adsorbate objects that we just created, can you create a workflow to calculate the absorption energy for these things? Okay, so I'll give you guys 1 minute to look into it. Yeah. Oh, sorry. Up. All right, so let's look at the documentation of this workflow, of this function, right? So this function, it requires a bulk structure, right? And then we don't have to worry about performing the bulk optimization, and then the adsorbates for this bulk structure. So now that we know the different things we need to pass in. And it's important when you read the documentation, right? So it's important to check what form they're in. So in this case, we see that the adsorbates needs a list of molecules, right? So it's denoted by the square brackets. So we can go back, right? We can have the plutonium as the first parameter for the structure, and then the adsorbates. So if you if you try to tab complete, right, for a parameter, you'll see that the absorb-based parameter will have an equal sign after it, so you don't have to worry about the exact spelling. And then remember, we need to pass in the absorbate as a list, because this workflow will also take into consideration different types of absorbates. However, we only have one. So, okay. Oops. And yeah, there's some warnings here, but there's some warnings here from Pymatgen. You don't need to worry about this. But we basically created this workflow that we needed, right? And just really quickly, right? If you want to display all of these workflows that you created, because here what you should notice is this new workflow. This new workflow is actually, I maybe should have named this something else. It should have been workflow S, because this is a length 3 list of workflows. And if you print what each one of them look like using the next cell, right, you see that there's one workflow for the 111 surface, right? Another workflow for the 110 surface, and finally a workflow for the 100 surface. So these are basically, these are kind of just 3 completely distinct surfaces of plutonium where you're going to try to calculate the adsorption energy, right? And once again, we can explore the workflows and kind of see what's actually going on inside of them, right? So one thing that you might notice is that in a given workflow, right? Let's open this one for silicon, for example. The structure that we're actually calculating is, sorry, whoops. Sorry. Oh, okay, no, it's not stored in this guy. Yeah, so the structure that we're actually calculating is going to be stored in one of the tasks, right? So here, what I'm doing is I'm converting the structure that's stored in the tasks of one of these workflows, and then I'm converting that structure into I'm converting this task into a into a dictionary, and then I'm converting the structure component of that dictionary, so this is one of the surfaces with the adsorbate that we'll be performing a calculation on, right? I'm converting that into a structure object, and then I'm viewing the structure object, right? So this is internally what this kind of get all slabs workflow is doing, right? It's kind of performing rotations of your plutonium and then finding positions to put this hydrogen molecule. Sorry, be able to scroll. Right, it's find different positions to put this hydrogen molecule. Right, so that's from workflow. That's from the fireworks number 2. Right. Oh, that's from workflow 0. And if you look at, this is the output from the first workflow. So this is a different facet of plutonium, right? We see that we have a completely different structure with the hydrogen adsorbate inserted somewhere else, right? So these are kind of what goes into your supercomputer before the calculations have been performed, their initial guesses. Okay, so there's a few other things that you can do. There's actually like a really wide host of different things you can do with Atomate, and we won't be able to get into all of them here. But just as a quick demo before we get into our final example, right? You can see that you can do this. You can do these HSE band structure calculations. So HSE is a much more expensive. Yeah.
Quick question.
Yeah.
In the workflow, there were no arrows. Does that mean all of those things can be run independently and they don't have dependencies?
Oh. Yes. Right. Yeah. So yeah, that's a good thing to note. Yeah. So yeah. So if you think about how an adsorbate calculation needs to be done, right? The information that you need is really the energy of the slab by itself versus the energy of the slab, but with different kind of positions for the adsorbate. So these calculations have nothing to do with each other, right? Except until you finally do the analysis, essentially. Okay. Okay, so let's say, okay, so one of the primary kind of shortcomings of traditional density functional theory is you have this underestimation of the gap, of the band gap of semiconductors. And you can basically do a, what is called a HSE, which is a hyperfunctional calculation to make up this difference. However, these HSE calculations, although they do provide you with the reasonably correct band gap, they're about 3 orders of magnitude more expensive than typical DFT calculations. So you can't really do them on your, it's hard to do them on the entire band structure, right? So if you look at this this band structure plus HSE workflow, what we've done here is we'll perform a initial structure optimization and then perform the same band structure workflow as you've seen before, but then it's going to take the band structure that's calculated on a high symmetry path through the Brillouin zone, identify the minima there, and then just using the information at that, using that specific K point, you can perform a single HSE calculation where you're just monitoring how that band gap can be corrected if you use this much more expensive functional. Right, so this is a low-cost way to get fairly accurate predictions of band gaps of semiconductors. And also, just kind of as a quick advertisement, there's also support built into Atomate for FEF, which is a computational spectroscopy code. And also, my office mate, Sam, has been building a lot of the infrastructure for running QChem, which is a localized basis quantum chemistry code that can be used to study molecules. Right? And then I'll just quickly demo what those workflows look like. Whoops. Okay. Yeah. So the FEF one is not much to look at. It's just this one operation. And then the quantum chemistry code, you see it looks very much like VASP because it's doing the same thing, right? It's doing a DFT calculation. Okay. All right. So as a quick aside, right? Because some of you might be kind of really familiar with VASP, right? And you might know the exact kind of parameters that you yourself need to run a particular VASP calculation. And you might not want to go through the trouble of kind of importing your own personal settings, right? And typing them out into a workflow each time and use the add modify incar operation, right? And also and there might be there might be situations where you might want to design something that's not really a completely new workflow, right? It might be some combination of the standard operations that have already been built into Atomate. So that's very much like the band structure workflow that I showed earlier, which is just a kind of series of discrete tasks that have already been implemented into Atomate, right? So what you can do is using this So using this get workflow from SpecDic utility, right? This allows us to essentially write our own version of a band structure.yaml file, right? Which then, like if we're doing many of these calculations, we can store this somewhere and then make sure that we have reproducible results. So I'll just go over really quickly how to do that. So this will be using some of the things that you're already familiar with, like JSONs, and basically we're going to design a function, right? We'll call it get custom workflow, right? And that's going to take a structure, it's going to take a structure as one of the inputs and a YAML file as the other input. And what this needs to do is it needs to read a local YAML file. So the way you read a YAML file is by loading it using this loadfn function. Right. So we'll be reading this cal-YAML. And then if you look at the documentation for this get workflow from SpecDic, right? I haven't imported it yet, but this requires a structure and the dict that you just read in from the YAML file. So this will give you a new workflow, and then of course this function will have to return that workflow. Right? Okay, so that's the base. That's all you have to do, right? And if you kind of want to have a slightly customized version of a optimized workflow, this is kind of a silly example. So I'm just turning one of the flags inside VASP. So this tells you how many spin channels you need to use in a calculation, and this really shouldn't affect the So basically, in systems with paired electrons, you could set this to 1 and save a little bit of computational time, but this really isn't something that's supposed to change the output of your calculation, right? And then I'm using the file magic command inside of IPython to write this into a document that I'll call opti.yaml. Right? So then this is so if you wanted to use this workflow in the future, you just be able to call this function with this file name as one of the parameters, and then you have your workflow. So okay, so that's kind of a quick aside. So now let's go into our final example, which is we're gonna create a Atomate workflow to analyze all of the different structures in the aluminum chromium system, and then submit them using the useFake VASP workshop, and then analyze those results. Right? So to accomplish this, we first get all of the structures inside this chemical system. Right? So if we can start with the so we'll be getting structures, right? We can start with all the systems, all the structures in the system that contains both aluminum and chromium. So npr get structures, and it needs the chemical system. So al-cr, right? And we can append. So if you think about how lists work in Python, right? So this returns a list of structures. We can add to that list with a additional query. So we want all the structures. Get structures. We want all the structures in the just pure aluminum system, as well as all the structures in the chromium system. Right? So if you run this really quickly and maybe take a look at the output for a quick sanity check, you have you have a large list of different structures here. Okay. So for a single structure in that list of structures, we could just use the get custom workflow function that we wrote earlier. So workflow is equal to get custom workflow structure, and then the name of that YAML file, so opti.yaml. Right. So remember, this just submits a single optimization firework onto our launchpad. If we run lpad.add workflow. Right. Whoops. Wait. Oh, wait, sorry. Did I? So I must have skipped lpad reset. Hold on, sorry. Yeah, I must have skipped a line earlier where I reset the password. So where I reset the database. So let's just go back up and run this over again, just for safety, I guess. All right. And then we need to make sure we modify this. Whoops, wrong box. Sorry. Yeah, we need to make sure that we modify this with the use fake vast workshop. All right.
Your get custom
Oh.
workflow function is not actually returning. Go back.
Oh, did I? Oh, thank you. There it is. Okay. Yeah. Okay, so if you run this, right, and you go back to your fireworks dashboard, right, you see that all these various chromium, aluminum, and aluminum chromium alloys have been submitted into your calculation database. And so using the commands in the next cell, we can run this really quickly. So run this, observe, right? So everything is working fine. We have one firework that you're going to have one firework that fizzled, right? So that was intentional in this case because it's just kind of to demonstrate what you can do in this kind of situation. So if you look, so basically this is to simulate the situation where maybe you hit the wall time of your simulation or something, and this particular firework broke, right? And if we look at this firework, this has this is a firework. This is a workflow with ID 3, right? So if this happens in real life, what we need to do is run lpad.rerun rerun firework, right, and pass 3 in as the ID. And if we go back to our dashboard, we see that instead of being fizzled, it's ready to be rerun now. Okay. So now that the calculations have finished, except that one, but we'll forget about him for now. All right, we can kind of analyze the results of our calculations. So the way Atomate works is it parses the contents of this db.json file, right? So if you look at it, in this case, it's kind of storing the, so basically, the results of the calculation are stored on a database that is specified by the contents of this db.json file. And it's really important that this file exists on all the different supercomputing systems that you might be running on. So, so in this case, we're just using the local host, right? And we have a database called MP Workshop, and everything will be stored, or everything was stored when we ran this into a collection called tasks, right? And one of the things we can do in that collection is we can basically query the results there using essentially our wrapper for PyMongo that's called Magma. So we import. So this just has some more convenient syntax for kind of our daily lives of performing high throughput quantum chemistry calculations. So we create the task database using this command, and then we have to connect to it. Oops. And then we can quickly query one item inside of that database. All right. Okay. So of course, sometimes this might be way too much information. Right? So one way to kind of look at what's going on here is if we say tasks.query query 1, right? So this will return one of these dictionaries, and we can just ask for the keys of that dictionary, right? So here we see that you have basically some metadata about the chemical system that you're studying, maybe the kind of a pretty formula for the chemical system, and then all of the various inputs and outputs of the calculation that you just performed, right? And this really allows you to kind of examine the data more slowly, so you can kind of go in here and say, okay, so if I wanted, so if this was, sorry, go down here. So doc is equal to tasks query 1, right? Doc chemsys will be the system that you're looking at. Okay. Okay. So if we specifically query, for things inside the so we can basically specifically query for things inside a given chemical system, right? So here I'm querying only for things in the aluminum system. However, to reduce the amount of data that has to be sent, I can basically only ask for the output properties, right? So this is how you would get data out of the database that you just populated. And we can write a quick script to get all of the outputs for the different chemical systems that compile for the different chemical systems in the aluminum chromium system. So if we look at, wait, hold on, let me. Oh, oops, that's the wrong one. Okay, so let's look at docs. Right, so if we want all the information in the aluminum chromium system, it'll be docs is task. You'll be querying with the criteria that you're in the aluminum chromium system. And then for properties, not only do you need the outputs, I also generally like to print to get the formula pretty. Oops. All right. And it's important to remember that right now this docs this docs just returns a Pymongo cursor. So if you call list on this, this will give you a list, and you can print all, and you can see that all of the chemical systems are inside of this docs list right here. So so we can get so we can basically repeat this for aluminum, chromium, and aluminum dash chromium. So let's just quickly do that. So say we first create a empty list that's going to host all of the different task documents, right? And for chemical system in aluminum, chromium, aluminum, chromium, right? We basically need to do the exact same thing. So we copy this down, right? And then the chemical system in this case will just be ChemSys. However, just because I know what analysis is coming up, we'll need the output and the composition unit cell. So this will give us a list of the tasks inside this chemical system, and then we will basically be appending this to our empty list at the beginning. So, oops. Okay, and oh wait. Wait. Oh, sorry. It's not append. So basically here, task query returns a list. So every time you want to add a list to another list, you need to use extend. All right, and if we do that and you look at the length of our tasks, we now have 11 tasks in the database, and basically the computed entry object in Python, and this I'll just quickly gloss over, is a way for us to keep track of both a chemical composition and a energy for something that was calculated with that chemical composition. So if we look at this particular task, right? So the task with index 0, we can take the output, the energy of the output, as well as the composition of the unit cell to create a new entry object that has those two properties. And we can quickly populate a list of computed entries using the task that we've just collected. So entries is a empty list. And for tasks inside our big list of tasks with aluminum and chromium, we need the energies, right? We can just basically copy this. And copy this here. Task should be singular, right? And then here, because we're creating a single entry each time, we'll just say entries append entry. Right? And this basically gave us all the different chemical compositions and their energies. And if we run the cells that follow, right, you can see that we can plot the phase diagram using the data that we just queried. Right, and so of course this only has 4 points on here, and if we tell it to show all of the unstable calculations as well, you see where the unstable calculations are. Okay, yeah, so that concludes this section. I think I'm a little bit over time, but thank you.